Hello. You should see the desktop and hear me. Does everything seem okay? Does it seem to be working?
Yes, I can hear you.
Okay, great. Oh, still a lot of people missing. Okay. So there's another programming assignment out. Okay. Let's let's start off by looking at it, though we're not going to say very much about it because it's based on what the examples we've been doing started the other day, recursive functions. So let me just like there's not much, it doesn't say very much here. Like the real instructions are in the zip file. Okay, so download the zip file, okay, and unzip it. Okay, and the homework is there. Okay, so open that file, and there's a description of a dozen recursive functions for you to write. There's 12 problems in here. Okay, so each one has a description of what the function should do. Some of them have an example of what the function should do. So there's a description. So, what the type looks like, a word description of what the function should do. And then some of them have an example of of an input and output. Okay. And then you write the result, and then you write your version here. Okay. Using the name that's given there. Okay. So you have to do 12 of these. And the other thing you have to do is you need to test your code. So there's a test program here. And this time I want you to write the test. So for example, like for problem one, okay, I gave you two examples. So might as well make those tests. Okay. So, and then make sure that you get those outputs. Okay. So make those tests. Maybe you want to do some more tests. Okay. Yeah. So you have to write the tests here. Now, obviously, if the problem's got an example, you probably should just take that example and make it the first test. Okay. Now, what you're going to do is then to when you the way you'll work on this is open a command prompt in here. Well, actually, what I want to do is I should put a shortcut to SML in here. Okay. Yeah, I put a shortcut to SML in there. Okay. Open a command prompt. Now, if you type SML, that's not really what I want. I want to use that shortcut. And at least in my case, the shortcut works better than typing SML. So what I do is I type SML and then hit the tab key because that shortcut's really called .link. See, it's got a little arrow down there. That file is really SML.link. And if I use that file, I get a slightly cleaner version of SML. Okay, so this is the shortcut that I copied out of the start menu. If you go down to the start menu, if you've installed SML with the installer, it puts itself, oh, it's not in this start menu because I installed it on my other account. I installed it using my other account, so it didn't end up in the start menu of this account. But you'd have SML here, and I essentially made a copy of the item that was in the start menu. So this is a copy of what was in the start menu here. Okay, and that it works better. Now, if I just open a command line and type SML, it does work, but it gives you all this stuff here. Yeah, I think it's the same version. I think it's the same version of SML. I think the people who wrote the installer didn't do quite a good job of it. So this link seems to be the right way to run SML. If you just open a command prompt and type SML, you get this kind of messy start. It's not a big deal, but see, it starts off with this kind of messy messages. I think it's the same thing. I think I'm not actually. I haven't tested it, but I think it's the same thing. But it looks to me like the people who wrote the installer goofed up a little bit. So the version of SML that they put in the path see, this is using what's in the path. That seems to be different than what they did in the shortcut. But to get that shortcut to work, the way I do it is I just copy that shortcut into every folder I'm working in. Okay, and then I can just type SML. Well, if you want .lnk, not. Let's see, what is it? Oh, I'm at the desktop now. I'm in the wrong folder. Yeah, in the folder that the homework 4 folder. Okay. Open a command prompt in the folder your work is in. Type sml.lnk. Okay. Oh, I forgot to short. I usually shorten the name to SML. Thought I did that already. I shorten the name to SML. SML dot LNK. There, see? Yeah. And you don't even have to type the dot. You can also you can type SML, hit the tab key, and Windows will complete it to sml.link. Okay, that uses that link remember, that's copied from the start menu into this folder. Okay, and then that link seems to work better than if I type SML without if I don't use the link, I get this kind of messy start. Okay, and if I use the link, I can either type SML and hit the tab key, or I can type just sml.lnk myself. Okay, but you have to have that link in the folder. Now, then you would say use quote homework4.sml close quote semicolon. That'll load your code. Okay, now my code doesn't load because there's no code in there. Let me make a little change in here. Let me delete. I can get these to load by just deleting all these things here. Okay, so I'm going to just to show you the steps, I'll delete all these. That'll make this thing load. Okay, now there's no syntax errors in there. And for the first function, I'll write something it's supposed to be a function that takes in a int, supposed to take in int char pair. So I'm going to, it's supposed to take in an int char pair and give you out a string. Okay, all right. Now there's a definition of a function. Okay, doesn't do very much, but there's a definition of a function. So then I go to the command prompt. Okay, and I load it. Okay, so there's my function. It takes in an int and a char and returns a string. Now let me put it. Now here's my test. Now I can load my tests. So now after loading the functions, I'll load the HM homework for my tests. Okay, load my tests. Okay, and my test failed. My function didn't process. My function failed. It did not. My function only works on the pattern 0, 0, and I gave it 5p. Okay, if I want, I can make it pass both those tests. Watch out. I'll make the program pass both those tests. I'll make it pass both those tests by just cheating. Don't cheat this way. With that input, I want to put out the output. Okay. So that's cheating number one. And then I'll make it pass the other test. Notice I'm making it pass the test by just repeating the patterns. But I want you to see what it looks like when you, so there's the other pattern, and I'll output, okay, right? So there's my function, there's my test. Go over here, reload the code. So I'll see now I'm using the up arrow and down arrow key. Okay, so I go back up. There's my load my code, loaded without error, load my test. I got what I wanted out. See, I got the right cheating one, cheating two. Okay, so then, yeah, after you've got a problem working, yeah, now when you load this file, you find out if you have compiler errors. So if you did something, if you messed up here, if you did something wrong, okay, I forgot a comma there. If I load that file, okay, I find out, I found out I got an error. See, I got an error from loading that file. Okay, so I got an error. So you can, you when you load your code, you'll get compiler errors, and then you shouldn't. Hopefully, your test cases won't have any compiler errors in them. And then you run your test cases, and you have to look at the outputs when you run your test cases. Okay, let me fix that. Fix the code, reload it. Okay, it loaded without error. And I mean, I got a warning, and warnings are important. You should pay attention to warnings. Okay, you should compile without warning. There's one warning we'll talk about later on that you can, that's okay. There's one warning that you can get when you in your code that is okay to get. But if you get match non-exhaustive warnings, you probably, probably should look into why you have them. Okay, so warnings, you should look into errors you have to fix. So load the code, then use the arrow key to load the test. You have to look at the output of the test to make sure they're right. Yeah, we're not using an automated testing framework like JUnit for Java. So your tests, you have to know what the output is. Like here, that should have been what the output was. That should have been what the output was. Okay, so you have to just, you have to look at the output of your test to see if they're the right things. Okay, now you could actually probably automate these. Um, Here's one trick you could do. Instead of using arrows like that, put an equal sign here. This would say that the value of this function should equal that, okay? And the value of this function is supposed to equal that, okay? Now, this will either turn out to be true or false. So let me reload the test. Okay. Notice I got false, false. Oh, I failed the test. So that's one way to more or less automate the test. If you should know what you're expecting out. So set the call the function and set it equal to what you're expecting out. That makes this a Boolean expression where the left-hand side is either equal to the right-hand side or not. And then you should see all trues in your output. Yeah, you should see all trues, and then you passed your tests. Okay, so that's one way to make the tests automatic. It's kind of a cheap way to make for automatic tests, but it works. Okay, you need to know what the test results should be, but you should be able to figure that out. See, like here I tell you what the output should be. Okay, so I can turn that into a test by taking that output, putting it there as an equal sign, and putting a semicolon at the end. Okay, now I've got a test that says when you call that function on that input, you want the output to be equal to that. And you'll either get true or false. You're looking for trues. You're looking for everything to be true. Okay, right? So you have to come up with the tests. I mean, not every function in here has some examples. Some of them, a lot of them do, but see, there's one that doesn't have any example. There's another one doesn't have any examples. There's another one doesn't have any examples. There's one that does have. I gave examples when I thought there might be some ambiguity in how the function works. So I'm when I do give examples, it's usually because I want to really make clear how because sometimes the words aren't enough. So I usually give examples of outputs when I'm trying to show you, make sure you know exactly how I think the function should work. Okay, so if I think the function's easy to describe, I don't necessarily give an output. Okay, but if I think there might be a little bit of ambiguity, I give an example, and that's the way a lot of libraries are documented that way. If you looked up ML's library or even Java's library, when they think functions are real straightforward, they don't give you examples. But if they think a function's a little bit tricky, the documentation will quite often have some examples of using the function. If they think there might be some ambiguity in describing the function, you can clear up the ambiguity sometimes by some well-chosen examples. Okay, so some of these come with examples, but not all of them do. So obviously, the ones that come with examples, use those as test cases. And then, but these will not be exhaustive test cases. They're meant to just show you, they're meant to make it clear to you what the function does, but that doesn't mean that they test your function well. You should be trying to test your function well. So you should try to come up with good tests. Usually with functions like these, 4 or 5 tests are almost always enough. 2 may not be enough. Okay, like for example, you should always test that you're doing the right thing on an empty list. Yeah, you should just make sure that your function does give you the right thing on an empty list. So if you think that the function should return the empty list on an empty list, make a test that says that. Okay, so I think as a bare minimum, like I never get, like here's an example, one where I did give you that the function with the empty list in should give you the empty list out. So that should be one of my tests, but whatever you think, okay, so now it's a test. Yeah. But that test should be in almost all your examples. Whatever you think it should return for the empty list being in. Now, it's not always going to return the empty list out when it gets the empty list in. Not all examples work that way. But you should probably always check on what to make sure that your function is doing the right thing on the empty list. Okay, so you have to provide the test. When you don't put your tests in homework 4, because I'll run your programs through my own set of tests when you turn them in. So I'm going to run them through my own really super exhaustive. I'll test everything with 1,000 different inputs, but I'll test your code with my tests. So I want to make sure, and that way everybody's being tested against the same test. But that means that your code, this file should only be your function definitions. And this is this is the way people work in ML. This is the code you're writing. This is the thing that tests it. Those are 2 different things. It's not a good idea to blur them together. So the code is in one file. The unit tests are in a separate file. Java is the same way. You don't put your tests in the file with the code. So you need 2 files in parallel to each other. Okay, this file is just this. The 2 files are the same. They have is I kept them in the same so you could keep track of where you are. There's the test for problem 1. There's where you put the test for problem 2. There's where you put the code for problem 1. There's where you put the code for problem 2. So I kept all of this stuff in the test file, kind of redundant, but it helps keep you help you keep straight where things go. Okay, want you to write your own test. Okay, and if you've tested your code well, you'll be pretty confident that your test that you'll pass my test. Okay, all right. So let's see. Any questions about the homework? We haven't said anybody. I'm not saying anything about the details of these problems yet. We're going to talk more today about recursive functions. So you need to read each one of these, and hopefully when we talk more about recursive functions, this stuff will make sense. But any question about mechanics of this yet? Any question at all? Okay, so I've wanted to just point out something. ML is a compiled language, and you're running a compiler over here. Notice that there's no notice that there's no exe files over here. The ML compiler is not the kind of compiler you're used to. It's doing all the compiling in memory. So when it compiles that file, the compiled binary just sits in memory. It actually sits in the memory of this program, of the interpreter, and then it runs it from within its memory. Okay. It's kind of a funny thing. It's not the way, it's a compiled language, but it's not like a Java compiler or a C compiler. A Java
Is it just in
compiler.
time compiled?
Pardon me?
Is it just in time compiled, you're saying?
Yes, which also, but see, Java is a just-in-time compiler too, but Java is two compilers, what they call ahead-of-time compiling and a just-in-time compiling. The ahead-of-time compiling is the thing that produces the class file. Then when you run the program, it does the just-in-time compiling, which compiles from the class file to the Intel binary code. The just-in-time compiler is compiling from Intel, from Java bytecode to Intel machine code. The ML compiler does the same thing, but it does everything in memory. So it's actually compiling from ML code to a form of bytecode. Then it's just in time compiling the bytecode to binary code. But the thing is, it does it all in memory. So you never see anything over here. You don't see any of its internal files. Now, if you wanted to, you could see them. I don't know if we'll actually even use ML that way, but you could use ML the way we use Java, where you compile your ML file to a file, and then you run the file that you compiled it to. There is a way to use ML in that fashion. Right now, we're using it in this REPL fashion, and the compiling is just being done in the memory of this thing. So it's doing the two-step compiling. It's doing the ahead-of-time compiling into a bytecode, and then it's doing the just-in-time compiling of the bytecode into machine code, but it's all done in memory. In the case of Java, the ahead-of-time compiling is creating the class file. Then when you run the class file, it does a just-in-time compiling into memory of the class file into machine instructions. Okay, so it's a little bit interesting that ML can do it. It's just doing it all in memory. You don't see the result of the compiler sitting over here. Okay, all right. So now, oh, and when you turn into me these two files, and this is the file that's all the this file here is for your reference purposes. All those the ones we're going to talk about today, a whole library of recursive functions to give you examples. When you're doing the homework, it's a good idea to study this because there's ideas in there that'll help you solve these problems. You're not supposed to solve these problems just out of the blue. Okay, yeah, I don't expect you to completely to cook up whole new whole ideas from recursive functions. The ideas you need to write these are buried in here. There are quite a few examples in here, 21 examples. They vary from very simple at the beginning, very simple, to medium, to at the end. The last couple are kind of hard. The last couple are pretty tricky recursions. Notice that there's more than 2 lines of code there. We start off with examples that are just 2 lines of code. Then we get to things that, like this one, needs a helper function. See, there's a helper function buried inside of there. Okay, so guess this one's still just 2 lines of code. A lot of them are just that. This one's 3 lines of code. Okay. Oh, these are 3 different ways of solving the same thing. So this is 3 different solutions to a problem. Okay, so actually a lot of them are only 2 or 3 lines of code. That's the same thing is true over here. Most of your answers here are 2 or 3 lines of code. I think there's only 2 of them maybe that need more than 3 lines of code. Out of the 12, there may be only 1 or 2 that need more than 3 lines of code. Doesn't mean that 3 lines of code are easy. You have to think. Yep, you really have to think. But read these examples. We're going to do more of them today, but read them, understand these, because once you start getting a sense of how these work, then you have a sense of what tricks to play when you do these examples over here. So you're not writing this in a vacuum. The idea would be to absorb these examples, the tricks that are used in these examples, you're not going to be able to copy any code from here to here, but you can copy ideas. Okay, definitely you can copy ideas, but you won't be able to copy code. Okay, ML doesn't quite work that way. Java's a language. Java and C are languages where you can do a lot of copying and pasting. It's just they're just kind of a different language than ML. In the case of ML, there are definite patterns to what's going on. You'll notice patterns of how I'm doing recursion here, but you're not going to be able to cut and paste code from here to here. But there's a lot of similarity between these problems and these problems. So if you understand the idea here, you can do these over here. Okay. So in the homework folder, I put the big collection of examples there, so that they're right there when you're working on these. Okay. All right. So now let's turn to the examples. Okay. The examples are here it's this file here. Here's the examples up on the web. Okay. So here they are there. I'm going to download them to this computer and want to look at some examples. Okay, so I'm going to download them. Okay. And I want to look at a number of examples. Now, another way to work, the way I'm going to work here is a little bit different than what your homework assignment is going to be. These are already written out. So what I'm just going to do is I'm going to open the REPL, and I'm just going to, like, when I want to look at an example over here, I'll just copy and paste it over here. That's an easy way to work. Yeah, for what we're doing here, this is probably the easiest way to work because the examples are already written, and I just want to use them over here. So I'll just have the REPL open here and the file open here, and I can just copy and paste. Now I can use that function. The length of the list, the length of that list is 5. Okay, right. So now I want to look at some of the examples here. Let's look at this example here. Oh, let's go to the beginning though. I hope this is useful. There's a way of thinking about recursion here. What we're doing here is we're writing recursive functions on lists. That's actually a special case of recursion. It's probably the single most elegant and famous example of recursion. It's kind of what makes recursion important. There's lots of functions that can be written recursively, but when you write functions on lists, you almost always use recursion because lists just beg for being done recursively. The reason is because this idea that the list itself is a recursive data structure. A list is something in front of the rest of the list. So a list is something in front of a list. Now here's written as a grammar. A list is either empty or non-empty. And if it's non-empty, it's something in front of a list. See, there's the recursion. Okay. I'm using the word list to define the word list. I have a recursive data structure. A list is empty or it's built up on a list. So in order to define the word list, I need to use the word list. I mean, it's really hard to describe the list data structure without using the list data structure as part of the definition. Lists are inherently recursive. Now, if you go back to Java or C, when you write the linked list data structure, you actually write it in a recursive way. You write the linked list data structure. You'll see that if you look carefully at, you open up your textbook to the chapter on linked list, and you look at the node for linked list, and you see that a linked list node points at a linked list node. Okay, a linked list node has a pointer to a linked list node, but it's the recursion's in the pointer. The pointer points at another linked list node. Okay, so a linked list node has a pointer to a linked list node, so it's inherently recursive. Okay, since the data structure is recursive, the most natural way to program with lists is write recursive functions. Okay, and what you do is, okay, here's the ML pattern that goes with this grammar pattern. The idea is you say, you tell your function what to do on this case of the empty list, and you tell it what to do on this case of the non-empty list. So the ML function looks like this. F of the empty case. Notice it looks a lot like that. F of the empty case. Well, you give it some appropriate value. Or, see, notice the same meta syntax. When we wrote grammars, we wrote them this way. When we write ML, we write it this way. There's a reason for that. The designers of ML specifically designed ML around grammar idea. They designed the language around this idea that this is how you describe data. This is how you write the functions that process the data. One of their geniuses was the way you describe things should be also related to how you program them. So your language for describing them looks a lot like your language for manipulating them. That was a stroke of genius, to come up with the programming language to be written in a way that looked like the data itself. For example, later in the semester, we'll process tree data structures. Here we're processing a list data structure. The tree data structure is another recursive data structure. We'll write down the description of a tree data structure, then the function that processes tree data structures will look a lot like the function, the description of a tree data structure. The function that processes trees will look like the description of trees. That's brilliant, okay? So a function that processes lists, well, on the empty list, you give it some appropriate value. And then if the list is not empty, well, you say what to do with the first item, and then you need a combined step with the function recursively on the rest of the list. Okay, so notice that the left-hand side looks like the description of the see, it's the left-hand side that looks like the structure of the data. The right-hand sides are what we do on that thing there. Okay, so on this thing here, we give it an output value. If the input's an empty list, we decide what the appropriate output value is. If the input is the non-empty case, something in front of the rest of the list, well, we decide what to do with the something, recursively process the rest of the list, and then figure out a way to combine those two things. What do you do with the first item? What you end up deciding is three things. What's the appropriate value for the empty list? What do you do with the one item in the list? And how do you combine it with, but then this is the part you don't choose, the recursive function on the rest of the list. And you just assume that it does the right thing. And you have to take your one, you take the thing that is what you do with this and combine it with the answer from here. Okay, that's the meta pattern of recursion on lists. Okay, and you'll be hard pressed to find anybody writing code on lists that isn't using recursion. If you look around the world, almost anytime you see somebody processing, even linked lists in Java, it's pretty common to write the code in instead of writing the code in a while loop, which a lot of people would, especially in an introductory data structures book. At first, they'll write the code using loops on the list. But then usually if you look at later in the book, there'll usually be a more advanced chapter where they switch to using recursion. Now, when you took the data structures class, I bet you didn't get to the recursion part of it. You may or may not have gotten to the recursion part of working with linked lists. I know when I teach the data structure class, a lot of times we don't get far enough where we get to the recursive processing of the linked list. Okay, so in the Java data structures class, you're more likely to actually use a loop to process the data structure, the list, but not in the real world. In the real world, people writing real world linked list code are probably going to be using recursion because it's just so much easier to write it that way. And in a language like ML, there are no loops. You may wonder what happened to the for loop. Well, there isn't one in ML. The reason is use recursion. ML was designed to be processing things like this, and ML does not want you writing a for loop to process this. And I can show you, I can give you umpteen reasons why you don't want to write loops to do this. If you wonder, like, why don't people just write loops? They're easier. I can give you lots and lots of good reasons why you don't want to write loops. And as you read more and more about functional programming and what people call declarative programming, and modern blogs on Java and JavaScript point this out a lot. you really want to avoid loops. Eventually, you want to learn how to program with as minimal loops as possible because they're problematic. That's where a lot of the bugs are. The bugs lurk much more in the loops than they do in the recursion. And that's what people have learned in the hard way. Like when they go analyze where was the bug in this program? Your company, you ship a product and you get bug reports. And Microsoft keeps databases of where the bugs are. They analyze the database and say, what's causing the most bugs? And the single most common thing for causing bugs is the null pointer. Yeah, that's the single biggest cause of bugs in code is null pointer. Okay, and then other cause loops cause bugs. Looping is kind of messy. If you think about a for loop, here I'll show you real quick. For int I equal 1, I less than 10, I plus plus. How many times is that loop? Real quick, how many times is that loop? Timed interview question. How many times is that loop? How fast can you answer that? 10 times? That's wrong. Doesn't loop 10 times.
9.
9 times.
9 times.
9 times. How many times does it loop now?
10.
How many times does it loop now?
10.
10,
How many times does it loop now?
11.
11. But you see where I'm getting at? What's the issue with loops?
Small mistake maybe gonna cost you an extra loop.
Yes, small mistakes can lead to huge amounts of trouble. Small mistakes can actually be really problematic to find. How many times does that loop? That's not a quick question. How many times does that loop? I would count it out. 0.
Yeah.
I'm going up by 3s. And the
Yeah.
question is,
Or
how many times can I go up by 3 before I hit 10? And if you think that's a
3
problem,
times.
pardon me?
Say 3 times would
I
go.
think it's 3 times, but I would work it out. How many times is that loop? Who knows? This is a big problem. This is a big problem. If you write a for loop and just ask, well, the most basic thing you can ask about for a loop is how many times did it loop? And the answer is, it's really hard. Now, let me show you what else is worrisome here. Okay. You think you really are clever and you can read a for loop. So you know that this thing loops 10 times. Okay. You think it loops 10 times. Now, 50 lines farther down the code, there's this. How many times does it loop now?
3 times.
I think, yeah, because it's essentially incrementing by 3s. Okay. So somebody shows you a loop and you want to know how many times it loops. How do you figure it out? How do you figure out how many times the loop loops? Simple question. Should be an easy freshman programming question. What do you have to do to solve that problem? Somebody writes a loop.
Look at the end of the I and divide by the I increment.
No.
Just a helper, like a helper counter.
No. Somebody gives you code. It's already written. Somebody wrote code. Now, the guy who wrote the code is the worst programmer in the company, but it's the code he wrote. And now somebody says, tell me how many times this thing looped. How do you figure out? The code's written down. It's staring you in the face. How do you figure out how many times it looped? What do you have to do to solve that problem? Can you solve it by reading that line?
No, you can't.
No. Can you solve it by reading that line too?
By itself, no, you can't.
No. What do you have to read to solve the problem?
The
You need
entire
to read.
loop.
Pardon me?
The entire loop.
The entire loop. Now, let me show you what else you have to read. You're not done yet. Now, what do you have to worry about?
That function changing the value of I.
Yes. Believe me, this is real code. This is all over the place. Now, to know how many times that for loop looped, not only do you have to read the whole body of the for loop, you've got to worry about that function, what it does to I. People write code like this in the real world. They really do write code like this. They'll write functions that have side effects on the thing they're looping on. Okay. ML decided that this is completely lunacy. Yeah, this is just nuts to design your language around this kind of stuff. It looks okay when you first learn it. And then after you watch somebody misuse it, you realize, boy, is that a bad idea. Yeah. Something's good if, you can't say, oh, it's great if you never misuse it. But the trouble is, as soon as you start misusing it, you can end up with nightmarish code. And people do end up that way. People misuse for loops all the time. ML found a way to avoid them. It's really hard to misuse recursion. It's really hard to muck up recursion. Okay, recursion turns out to be way easier to analyze. And in fact, it can be pretty much kind of shown as a theorem even. Recursive functions pretty much do what you think they do. Loops do not do what you think they do. Loops, you have no way of knowing what a loop is going to do. There's just too much going on, too many side effects for you to actually know what a loop is doing. Okay, function calls can change the loop variable. Any line of code buried in the loop can change the loop variable. And people do this stuff. Believe me, they really do. You can't, they just write. Sometimes these tricks are meant to make the code efficient. So sometimes these tricks are there to make the code super fast. Okay. The most famous example of an insane piece of programming is Duff's device, where a guy thought that if he would, he mixed a while loop with a case statement. This guy, it's kind of the code here is kind of, it's hard to read, because what somebody did was he realized that if he nested a case statement inside of a while loop in a really weird way, he could write code that's super fast. And this was done in computer graphics back in the 80s. I think he invented this. And it became really famous. It's an insane piece of code that's highly misusing the idea of a loop and of a while loop and a case statement. But this guy realized that if he blurred a case statement and a while loop together, he could end up with really super fast code. Good luck reading it, but it's super fast. And it became so famous, it got named after him, Duff's device. And, it's an abuse of loops for the purpose of making code fast. But the result is you end up with unreadable code. You end up with something that's very hard to figure out, but it's fast. It's much faster than it would be if you fixed it. If you wrote it a nice way, it would be twice as slow. So Duff's device is famous for writing a bizarre loop that does a weird manipulation of the loop index in order to speed up the code a lot. Now, some people think that's great, and he's famous for it. But at the same time, other people looked at it and said, this is clearly why languages like C are a problem. You shouldn't be able to even do this kind of stuff, because you're writing code that it's very hard to understand. No one's ever going to be able to prove that your code is correct. And this is not the direction we want programming to go. We want speed to come from the architecture of the CPU, not from bizarre tricks of the code. Okay, so programming languages like ML were a reaction to that. Recursion turns out to be a good replacement for iterating. Recursion's a good replacement for iterating, especially when your data structure matches the recursion. Okay, that's one of the key ideas. Is here the data structure is recursive, so the function that matches it is recursive. Okay. All right. So now, when we look at the examples here, pay attention to these two lines of code. What you want to do is say, what am I doing on the empty list? What do we do? What do we return for the empty list? When the list is not empty, what do we do with the one item that we know is in the list? And how do we combine it with the recursive call on the rest of the list? This is supposed to be the right answer. We're assuming that this is going to give us the right answer. So how do we take that one item and combine it with the right answer on the rest of the list? Okay, like a simple example like length. The length of an empty list is 0. If you give me a list with one item in it, well, the length of that list is 1 more. Now there's the answer to this guy. Count him. What do I do with him? I don't even care what he is. I count him as 1. Then here's the length of what's left. So of course I add 1 to that. That's my answer. So the plus is the combined step. There's the recursion, which is going to correctly give me the length of the rest of the list. And I want to bump it up by 1. So the do something with the X, in this case, is just counted as 1. Okay. What if I want to add up everything in a list? Not much different. Now, adding up all the numbers in the empty list, they add up to 0. Okay. If you give me a number at the front of the list, what I want to do is add up the rest of the list and add that number to the rest of the sum of the rest of the list. That's the combined step. What I do with X is just keep him and add him to the rest of the list. Okay. The recursion is supposed to properly compute the sum of the rest of the list. Okay. Now let's look at one down here. It's a little bit more interesting. ML has a function called explode. Explode takes in a string and gives me out a character list. See, if I ask ML, what is explode? So I type the name of the function semicolon, and it tells me it's a function that takes in a string and gives me back a character list. Now it doesn't tell me how it does it, but it tells me what it tells me that the function takes in a string and gives me out a character list. So if I try it, explode of the string cats is the list CATS. Okay. Then there's an implode function. Now implode's built into ML that does the opposite. It takes a list of char and returns the string. It slaps the characters together into a string. So this problem here is to write implode. It's simple. We write our own version of implode. Okay. So instead of using ML's built-in implode, we're writing our own implode here. Okay. So what does implode give us on an empty list? Should give us the empty string. And we can check over here. That's what ML's will. If you implode the empty list, oops. If you implode the empty list, you get back the empty string because there's nothing. Notice that you don't produce the empty list on the empty list. You produce the empty string. Okay, now suppose I give you a list that has something in it. So there's the first character in the list. There's the rest of the list. You want to implode the rest of the list. Okay, that's what you should do. Then concatenate it with the stringifying of that character. Now, ML won't let you just do, like C would let you just concatenate the character at the front of the list string. ML won't let you do that. If you take a character and you try to concatenate it on a string, ML will tell you that's the wrong type. You can't concatenate a character on a string. ML doesn't do like Java will conveniently convert the character to a string for you and then concatenate the two strings. So Java will, I think it said, Java would conveniently convert the character to a string and then concatenate the string with the string. ML, remember we talked earlier, it never automatically converts anything. Okay, so ML never converts things. So it's got a function, str, that takes in a character and gives you back a string. So you have to stringify the character. So over here, now over here, what I do with the first, remember, we go back to the pattern. The pattern was do something with that first item. Well, now my do something with the first item is stringify it. And my combined step is the concatenation operator with the string that this thing returns. Okay, so down here, stringify that first item and concatenate it with what implode does to the rest of the string. Now here I show you an example how it works. So suppose you're going to implode that list, DOGS. Okay, step through the recursion. Here I wrote it out. So the first step would take this guy here and stringify it, and then it'll concatenate that with the imploding of the rest of the list. Okay, so there's one step. Now, you can't do this concatenation operator yet because there's no string on the right. There's this function on the right. So you have to do this function before you can do that concatenation. So ML does that function. But what that function does is it takes the first thing in the list and it stringifies it, and it concatenates it to imploding the rest of the list. So I'm working my way down the recursion. Now, you still can't do that concatenation because you don't know what this guy is. Okay, and so this concatenation is waiting for this guy, and this concatenation is waiting for this, so that you continue into the recursion. You implode something by taking the first item, stringifying it, concatenating it with implode on the rest. Okay, you implode that thing by taking the string of the first item, imploding the rest. Now we finally got to the end of the recursion. When you implode an empty list, you get back the empty string. Okay, so imploding the empty list gives us the empty string. Oh, now I can concatenate those two together and get S. Now I can concatenate those two together and get GS. Now I can concatenate those two together and get this. Notice that this was the recursion. See how the recursion gave us what we wanted. D in front of the recursion on the rest of the list. So the last answer would be DOGS, dogs. Okay. So now you don't actually have to think through all these steps. It's a good exercise, especially when you're learning this, to actually work your way through what this does in all the recursion steps. But the key thinking idea is that this thing does the right thing. So when you want to write this function, you say, I want to stringify the first item and concatenate it on the imploding of the rest of the list. Yeah. So I just think stringify this, concatenate it on to the right thing. And the right thing is that. So I'm taking D and implode and concatenating it to OGS, and I get the right answer. So you learn to think on, you trust the recursion to do the right thing. Okay. So you write your function where when you get to the recursion step, you trust it to do the right thing. And you just want to say, given that this is the right thing on the rest of the list, what do I do here to finish the problem? I only have to do this one last thing. This guy's going to do most of the work. I'm responsible for just this piece here, which is what I do with this first item. Okay. And from that point of view, recursion can be simple recursion problems are pretty easy to handle. This would be way harder to write as a loop. If you wrote this as a loop in C or C++ or Java, it actually would end up being probably a little bit more complicated. And then when you write in a loop, you have to start worrying about, starting values, ending values. The loop actually has a lot more places where you can mess it up. Okay, now let's look at another example. Suppose I want to find the maximum item of a list. Okay, so I want to find the maximum item in a list. Okay, now this one, first, let's jump to the recursive step. Skip this one for a minute. If I got a list and here's some number at the beginning of the list. Now I want to find the maximum of the whole list. What I really want to do is find the max of the X with the max of the rest of the list. So here's the recursion. I've got this recursion. It'll do most of the work for me. It finds the maximum of the rest of the list. And I just assume that it knows what to do. So it gives me back the maximum of all the other numbers. And then I want to know, is my first number more or less than those? That. So I take the max. Now I'm using ML's built-in max function that takes the max of two numbers. The built-in max function in ML takes the max of a pair of numbers. It doesn't take the max of a list. It takes the max of just a pair. So I'm going to use their max to build my recursive list max. So I'm using a library function to build a more general function. So I'm going to go ahead and use their library function that takes the max of two things. Okay, and then the second thing is my recursion function working on the rest of the list. Now, at this point, I haven't finished it yet, but I assume it works. See, my thinking is that I'm building this function. I'm assuming that it's going to work when I'm done. So it will know how to find the max of the rest of the list. And so I want to find the max of the first number in the list and the rest of the list. That's my answer. Now, if you think in the pattern here, what am I doing with the first thing in the list? Just keep it. I'm finding the max of the rest of the list. And the combined step is the step that says take the max of this thing and this thing. So I'm still working with this pattern, but the max is a function. The combine is a function, not an operator. See, a lot of times the combine was an operator that sat in between them. See how the combine was an operator that sat in between? Well, okay, the combine isn't always going to be an operator. Sometimes the combine is a function. So sometimes, like, I could have rewritten this this other way. Another way to have written that was as using function notation. I'm going to combine that thing with that thing. Okay, that's just another way to think about it. When you give me something in front of the rest of the list, I combine. I'll say I combine somehow, as there's a function. Now there's a combining function. In our case, down below is max. Combine the something with the first item with the recursive result of calling the function on the rest of the list. So here's the recursive call on the rest of the list. Here's the something I did with the first item, and I want to combine those two results. But this is using function notation. This is using operator notation. Quite often the combines are done operator-wise, like plus, concatenate, cons. But sometimes the combining is done as a function, like max. So we have both these. There's two ways to, like, so if I want, I can write this pattern. Okay, there's the pattern written operator wise. There's the pattern written function wise. And it's just, it's not a very deep difference. Sometimes you use an operator, sometimes you use a function to do the combined step. Okay, so the combined step can be operator or function. Down here, it's operator. Here it's operator. Here it's operator. Again, operator. Here it's another operator. But now here it was, the combined step was function. Function of the thing that was the first item in the list and the recursive call on the rest of the list. Okay, so that's a slight variation. It's still the same pattern, but all I've changed is from using an operator to using a function. And then here's what it looks like when you work it out. I want to take the max of this list. So what am I going to do? I'm going to take the max of, now, this max here, I probably shouldn't have written it that way, because that's not the recursive max. I really should have said that's the max from the library. That's the library's max function, not my recursive max function. And then over here again, that is the library's max function. Okay. No, I'm sorry. That one is the recursive one. See, you have to be careful. That one's the recursive one. Now, so I take the library max of the first item of the list with the recursive max of the rest of the list. Now, this function can't do anything yet because it doesn't have both its operands. It's only got that operand. That operand needs to be computed. So call the recursive function. The recursive function takes the int max of 6 with the recursive max of the rest of the function of the list. Okay. Now, this max can't be evaluated yet because it doesn't have that operand. Now, this max here was the int max. Okay. How do I find the max of 2, 5? Well, I find the int max, the library max of 2 with the recursive max of the rest of the list. Okay. Now, this max here is the int max, and so is this one. That's the int max. Okay. How do I find the max of that list? I take the int max of 5 with the max of the empty list. Now, here's where things get interesting. What is the maximum item in the empty list? Well, you can't return the empty list because you're supposed to return a number. So what number is it that's the maximum item in an empty list? And this is actually a logic problem. The right answer is it's negative infinity. Because the maximum number in a list is supposed to be the number that's larger than anything in the list. It's supposed to be the smallest number larger than everything in the list. Like, let me give you an example. What's the maximum in the list? 3, 7, 9, 2. Okay. Well, is 12. Well, 12's larger than everything in there. So what's the max? Well, 12's larger than everything in there, but so is 11. So is 10. So is 9. But 9 is the smallest number that's larger than everything in the list. So I want the smallest number that's larger than anything in the list. That's what the max is. The definition of max is it's the smallest number that's larger than anything in the list. Now, what about what's the max of the empty list? Okay. What's the smallest number that's larger than anything in the list? Well, for example, is negative 12 smaller than everything in the list? No, is negative 12 larger than anything in the list? Well, yeah, there's nothing in the list, so negative 12 is larger than it. So is negative 20. So is negative 2,000. So is negative 2 million. So is negative 2 billion. Notice I'm getting smaller and smaller numbers that are larger than anything in the list. Well, this is larger than anything in the list because there's nothing in the list. So it's true that it's larger than anything in the list. Well, what I really want here is negative infinity. Okay, and if you look in a logic textbook, you'll learn that the maximum of an empty list is negative infinity. The minimum of an empty list is positive infinity. Because that's the largest number that's smaller than everything in the list. Okay, so the max of an empty list is negative infinity, and the min of an empty list is positive infinity. Okay, this is a weird. This is kind of it falls out of analysis of the logic. You know, you want the max means the smallest number that's larger than everything in the list. Okay. The max is, okay, and the minimum is the largest number that's smaller than anything in the list. Okay, think of it. The minimum is the largest thing that's smaller than everything in the list. Okay, on an empty list, that'd be positive infinity, because positive infinity is going to be larger than anything that's in the list. Okay, now how do you do that in ML or C or C++ in Java? Every one of these languages has someplace in the library where there's a constant that's the smallest possible. It's essentially, it's not negative infinity because numbers can't represent infinity, but there is a smallest integer value. Okay, so what I want my answer to be is, remember, I want my answer to be negative infinity. So what I'm going to use is, instead of negative infinity, I'm going to use the smallest int. Okay, so I don't have infinity available. So what I'll use is the smallest available int. Okay, and here instead of plus infinity, what you use in C and C++ and Java is the largest available int. Now, why do we just say the largest available int? Because the largest available int depends on whether you're on a 32-bit computer or a 64-bit computer. Not all computers have the same size ints. That's why you want to use a library function. The library function keeps track of, on your computer, what is the largest int and what is the smallest int. Okay, so you're supposed to use the library's answer to that. And if you look it up, C++ has a library number. In the case of Java, it's in the integer class. Okay, if you go look in the Java's integer class, I don't remember where it is in C++, but in the Java's integer class, see, int max value, int min value. They're constants in the integer class. Okay, yeah, yeah. They tell you now. In Java's case, they know what it is because Java defines what an int is. It's 32 bits. In C, an int is not 32 bits. An int is whatever the compiler wants it to be. So this is more important in C than in Java, because in C, you don't know what the largest int is. The compiler knows. But in Java, the largest int is 2 to the 31 minus 1. But it's nice to just have that value defined. Okay. In ML, that value is in the library. It's val of int.minint. Okay, so that's what we set. The maximum of the empty list is essentially acting as, if you want, I can say it's acting like positive infinity. But it's not positive infinity, but it's acting like positive infinity. Okay, so that's my answer down here. What do I do when I get to the end of the recursion? What should be the maximum? Now, see, now here's why that works. Oh, no, I'm sorry. I wanted that's the negative infinity. I want the minimum int. Because see, now watch what happens. This guy is min int. Now see, I'm comparing it with, now notice that this will always give me this guy. That's why I want to put negative infinity here, because I want to get the right answer at this next step. What's the max of 5 with this thing? It should be 5. So this thing needs to be negative infinity, because I don't know what it could be here. I could put any number I want there. I could make this number negative 5 gazillion, and I still want this to give me the right answer, that the max of negative 5 gazillion and min int is that number there. So this number has got to be smaller than anything. See, here's the logic. This number better be smaller than anything I write there. Otherwise, I won't get the right answer here. So this has got to be smaller than anything I put here. So this has got to be the minimum int, or negative infinity. So there's a practical reason why this is the right answer over here, that the max of an empty list is negative infinity. Another reason why you want it to be negative infinity is so that the max function gives you the right answer. So that the max function gives you the right answer. The max function on 5 and the max of the empty list should give me 5. So the max of the empty list needs to be the minimum possible int. Okay, so then it doesn't matter what I put there, I'll get back that number there. Okay, so that's tricky. You know, that's a tricky little piece of logic. That's got nothing to do with ML. That's same in the Java version of Max and the Java version of Max and the C++ version of Max. They all do this trick. The max of an empty list is negative infinity. In fact, what it really is, the max of an empty list is the most negative integer. and the min of an empty list is the largest integer. Okay, now once I've got this guy here is 5, now I can figure out the rest of the maxes. Oh,
So this max is library max.
yeah,
the
I
last
should put
three.
it, yeah, let me put in which ones are library maxes. That was recursive, that was library. This one is library max, library max, library max. Yeah, that's important. I should have fixed that. I'll update the code because that's because you got to tell the difference between the library one and the recursion one. So there's the, recursion one takes in a list and the library one takes in a pair. Now, in a sense, you could say it was clear because the library one takes in a pair, the recursive one takes in a list, but it's probably better to write it out like this. Yeah, that's the library max. So when I come out of the recursion, I come out of the recursion doing the library maxes. Okay, so the max of 5 and the minimum int is 5. The max of 2 and 5 is 5. The max of 6 and 5 is 6. The max of 3 and 6 is 6. Notice I can work my way out of the recursion. Okay. One thing that's a little bit interesting, if you go back to the pattern says to do something with the combine of this and this. This combine usually isn't going to be done until after this recursion returns. Yeah. So this gets left pending until this one is complete. But then by recursion, this thing is another one of these. So we see how this thing stays pending until this one is complete. And you build these big chains. Okay. Now, this big chain has practical importance. Suppose I'm taking the max of a list of 1,000,000 numbers. That means I'll have 999,999 pending int maxes before I get down to this last one down here. Okay, that's actually real important. That's actually where recursion has a problem. Because if I'm taking the max of a list of 1,000,000 numbers, I have to have 999,999 pending int maxes before I get down to the last recursive max, and it returns min int. And at that point, I've got 1,000,000 of these int maxes to undo. That takes up a lot of stack space. That's why you hear people say that you shouldn't use recursion. Okay, and there's a way to solve that problem. Okay, so this is a problem with recursion. The int max, this max function wouldn't work on a list of 1,000,000 items. It probably wouldn't work. I would probably run out of memory space. If it worked on a list of 1,000,000, it won't work on a list of 1,000,000,000 or a list of 10 billion. At some point, I'll run out of stack space. Okay, that is where recursion has its trouble, that it builds up these long stacks of things to do. But there is a solution to that. It's called tail recursion. So later on, we'll see that there's a way to solve this problem also, where you can have your cake and eat it too. You can use recursion, and you don't have to worry about these big stacks of pending things to do. That's what loops have an advantage. The loop doesn't have pending work to do, but recursion has undone work that's still pending. Work that needs to be done after the last recursion is finished. You need to undo all these guys. That is a problem if you're trying to process huge amounts of data, but it can be solved by using a special form of recursion called tail recursion. Okay. All right. Now, let me show you one more. I won't finish it, but I'll show you. After 5 and 7, there's a group of problems here, 11, 12, and 13, that are very interesting. We'll after spring break, we'll come back and we'll do these. Like, look at 12. It takes in 2 lists. It does recursion on 2 lists simultaneously. It does recursion on, no, I'm sorry, not, this one takes in a list of pairs, and it does recursion 2 at a time. Yeah, this one does recursion on a list, but in pairs. So instead of pulling one item out of the list, it pulls two items out of the list. That means you need two base cases. So we'll go through. So this is, you can read this over the break if you want, but we'll pick up on this when we come back. This one needs two base cases because it's pulling things out of the list two at a time. Then this one's interesting because this one recurses on both a int and a number. Okay, so this one's going to recurse on an int and a number. No, I'm sorry. No, I'm sorry. This one recurses on two lists. This one recurses on two lists. Okay, so this one recurses two items at a time. This one recurses on two lists simultaneously. And then this one recurses on a number in a list. This one recurses on a number in a list. So the patterns start getting a little bit trickier. So the recursion starts, we start kind of diverging away from this simplistic pattern that we set up here. And for example, we might take two items out of the list at once, okay? Or we might have to recurse down here on two things, okay? So item 11 recurses two items at a time, 12 recurses on two lists, and 13 recurses on a list and a number. So we want to look, so those are slight variations on the pattern. And that's where things get a little bit interesting. So up until 11, everything is the same kind of pattern. The first 10 of them are the simple pattern, the basic pattern. Okay, so then starting with 11, remember, starting with 11, things start getting a little bit tricky. Yeah, I'm pulling two things out of the list at once. So I need two base cases. Okay, and then so that's where we'll pick up the slightly more challenging cases. And in the homework, I mix things up. In the homework, there are some of the more challenging recursions. Not everything is a simple recursion. Some of the homework problems are this pattern of real simple recursion, but some of the homework problems have this little bit of mixed up thing. You might have to recurse on two lists, or you might have to recurse two items at a time from a list, or you might have to recurse on a number instead of on a list, or a list and a number. Okay, so we'll do, when we come back, we'll do 11, 12, and 13. Those are the real interesting cases. And then after 13, it's just everything's a little bit different. All these examples are the slightly harder ones that are a little bit different. Okay, actually, some of them are real easy. Like there's only 2 lines of code. Okay, it actually is. Now it's recursing on a number and a list, but it's still only 2 lines of code. Okay, all right. So we'll quit there. We've run out of time. If you have questions about the homework, if you want to look at the homework is due in 3 weeks. Okay, it's due down here. Not when we come. It's not the week when we come back. It's the week after we come back. So it's due. I made it due the 30th. Okay, almost 3 weeks. Okay, so if you want to look at it over spring break, feel free to ask me questions. If you have questions about the homework, if you're curious, you look at it over spring break and you have questions, send me email. I'll answer emails over the spring break. But the assignment's not due until a week after spring break. It's due the 30th. So if you don't want to work on it over spring break, I think you'll have time to do it afterwards. So if you do want to look at it, if you do want to play with it over spring break, feel free to ask if you have questions about it, okay? And so have a nice spring break. Anybody got any last question? Any last question before we quit? Okay. So I hope you enjoy your spring break, and we'll quit there. See you in a week and a half. Bye-bye.